Hey, it's pretty mind-blowing how much deep learning is kind of woven into our daily lives, right? Especially for Gen Z.
Oh, absolutely, yeah.
Like, think about it. Scrolling TikTok, does it ever feel a bit eerie how the algorithm just knows what you want to see next?
Or your Spotify rap being like scarily accurate.
Totally. That's deep learning, flexing its muscles.
Yeah, and it's even like behind the wheel of those self-driving cars you hear about, Waymo, Tesla.
Right.
But it's way more than just, targeted ads and playlists.
Oh, yeah.
Definitely.
Yeah.
Deep learning's powering instant content translation now, connecting people across languages. It's pretty amazing.
Wow.
And who could forget AlphaGo, beating the world champion at Go?
Oh, yeah, that was huge.
The free code camp crash course we looked at points out Go has more possible moves than atoms in the universe. Insane.
More than atoms.
Seriously. So that win wasn't just about a game. It showed a machine mastering something super intuitive, strategic, stuff we thought was just human. A big signal for AI's potential.
Wow. Okay. So today we're going to dive deep into this deep learning thing. It's clearly shaping our world now, and it's going to be like a massive deal for the future. So the plan is to break down the basics, but skip the super dense jargon, right? So you can actually get a handle on what it is and why it matters.
Exactly. We're using the transcript from that deep learning crash course for beginners on freecodecamp.org. It's a really solid source for getting that foundation.
Perfect. So our mission today, pull out the key ideas, explain how it works, touch on the cool uses, and maybe some of the tricky bits too.
Sounds good. All tailored for someone curious, like our listeners.
Exactly. Think of us as guides. Okay, let's unpack this.
Yeah.
Where does deep learning even fit in the whole AI picture?
Good starting point. So imagine nested circles. Russian dolls? Maybe.
Okay.
The biggest circle is artificial intelligence, AI. That's any tech that lets computers mimic human smarts. Includes older stuff too.
Got it. Big circle AI.
Inside that, you've got machine learning, ML. That's a subset of AI focused on teaching computers to learn from data without being explicitly programmed for every single thing. It's about pattern recognition.
Okay, so ML is computers learning patterns from data, so deep learning is.
Right, deep learning is then a subset of machine learning. It takes that learning from data idea even further, learning representations directly from the raw data itself.
Ah, okay. So AI, machine learning, deep learning, like those circles.
Exactly. AI is the big goal, ML is one way there, and deep learning is a specific, pretty powerful technique inside ML.
That nested circles thing really helps. Now, that free code camp course uses a great example. Telling cats from dogs. Why is that hard for computers?
It's perfect, right? Humans, easy. But teaching a computer, well, with traditional programming, you'd have to painstakingly define features, like pointy ears means this, certain tail wags mean that.
Ugh, sounds impossible. How do you even define pointy in code?
Exactly. It shows the limits of older machine learning. It needed so much human help, what we call feature engineering. Now, to see why deep learning is such a leap, it helps to look back at some early AI and ML wins. The transcript mentions a few big ones.
For sure. Let's start with 1997, IBM's Deep Blue. Why was that a big deal?
1997 was massive. Deep Blue beat Garry Kasparov in chess.
The world champ, right?
Yep, the reigning world champ. First time a computer had ever done that. Showed AI was getting seriously powerful.
Okay, major milestone. Then, fast forward to 2011, IBM's Watson on Jeopardy.
Right. Watson took on the human champs, Ken Jennings and Brad Rutter.
And won.
Yeah, won the $1 million prize. And Jeopardy's tough needs, language understanding, context, tons of knowledge, showed a different kind of AI smarts.
$1 million definitely says something.
Yeah.
Okay, then 2015, AlphaGo. That felt different somehow.
Totally. Google DeepMind's AlphaGo beat Lee Sedol, an 18-time Go world champion.
Yeah.
And Go. Its complexity is just nuts.
That's the one with more moves than atoms.
That's the one. People thought AI mastering Go was decades away, maybe impossible.
Puts it in perspective. Machines weren't just playing games, they were kind of redefining limits.
Exactly. And like the video transcript points out, deep learning's impact goes way beyond games now.
Right. You see it everywhere.
Definitely. Self-driving cars, fighting fake news online, even things like predicting earthquakes. These breakthroughs open the floodgates.
So back to basics then. After all that context, how does the transcript actually define deep learning?
It gives a pretty clear definition. Basically, it's a machine learning technique that learns features and tasks directly from data. It does this by running inputs through neural networks inspired by biology.
Neural networks. We'll get to those.
Yeah, and the key idea is going deep. These networks have multiple hidden layers, letting the machine build up complex connections and figure out how much weight to give different inputs to get the best results.
Going deep. Makes sense. So what was the big problem with the older machine learning that made going deep necessary?
Well, the material highlights that traditional ML, even sophisticated stuff, still needed a lot of human expertise baked in. They were kind of limited.
How so?
Take face recognition. With older methods, you had to tell the computer what makes a face, eyes, nose, mouth, and define those features in ways a computer gets, like specific lines or shapes at certain angles.
Sounds like a massive headache.
It really was. Deep learning flips that. The algorithm learns the important features itself from raw data. Feed it tons of face pictures, and it figures out edges, then shapes, then eyes, then noses, and eventually puts it all together.
Whoa. So the machine does the feature finding on its own?
Pretty much. It learns what's important directly.
That's a huge shift. Like the machine is doing its own research. Okay, but if the basic ideas for these deep learning models were around earlier, why the big boom now?
Great question. The transcript points to three main things hitting at roughly the same time.
Okay.
First, just the sheer amount of data available now. Big data. These algorithms are hungry. They need tons of data to train effectively.
Right, we generate so much data constantly. What else?
Second, much more powerful hardware. The computing power needed just wasn't there before. GPUs, graphics cards, basically turned out to be amazing for this stuff. And now specialized chips, like TPUs.
So more data, beefier computers, anything else?
Yep, third key. Open source software. Frameworks like TensorFlow from Google and PyTorch from Facebook have made it way easier for people to actually build and deploy these models.
Ah, so the tools got better too.
Exactly. They offer pre-built components, making it much more accessible. So, big data, powerful hardware, and user-friendly software, that combination really lit the fuse for the deep learning explosion.
Makes sense. Okay, we keep mentioning neural networks. Let's dig into that. What are they? Why are they the foundation here?
Neural networks are totally the heart of deep learning. And as the source mentions, the inspiration comes straight from the human brain.
Like biological neurons.
Kind of, yeah. Our brains have billions of interconnected neurons. Artificial neural networks use neurons as their basic building blocks too. They take in data and through training learn to spot patterns and make predictions or classifications on new data.
Okay, inspired by biology. How do these artificial ones actually work together? What are the parts?
Well, information flows through a few key parts. You get an input layer, an output layer, and then one or more hidden layers sandwiched in between.
Hidden layers?
Yeah, and having multiple hidden layers is what makes it deep learning.
Input, hidden, output.
Got it. So how does the network actually learn from data going through these layers?
It's mainly a two-stage process. Forward propagation and back propagation.
Okay, forward first. What happens there?
Forward propagation is the data flowing through from input through the hidden layers to the output layer where the network makes its prediction or classification.
Walk me through that flow. What's happening inside? Okay. So the input layer takes your raw data, maybe pixel values from an image or words in a sentence. Each piece of input data is represented by an input neuron.
Right.
These input neurons are connected to neurons in the first hidden layer. Each connection has a weight associated with it. Basically a number indicating how important that connection is.
Okay, weights show importance.
Then for a neuron in the hidden layer, it sums up the values coming from all the connected input neurons, multiplied by their respective connection weights.
A weighted sum.
Exactly. And then each neuron in the hidden layer also adds another number called a bias. Think of it as like an offset.
Weighted sum plus a bias, then what?
This result, the weighted sum plus the bias, gets passed through something called an activation function.
Activation function.
Yeah, it's usually a nonlinear function. It decides whether that neuron should fire or activate strongly, and what signal it should pass on to the next layer. This repeats through all the hidden layers.
Yeah.
Finally, the output layer gives the result, often as probabilities for different classes.
Okay, so weights, bias, activation function. That decides the signal flow going forward. Makes sense. Now, what's this back propagation part? Sounds like going backwards.
It is. Back propagation is where the actual learning happens. It's essentially running the process in reverse, from the output back to the input.
Well, what's flowing backwards? Not the data, right?
Good question. It's information about the error.
Error?
Yeah. After the forward pass, the network makes a prediction. We compare that prediction to the actual correct answer, the label in supervised learning. If it's wrong, we calculate how wrong using a loss function.
So it calculates its own mistake.
Exactly. The loss function quantifies that mistake, that difference between predicted and actual. And that error information is what gets sent backward through the network during backpropagation.
Okay, so the error signal goes back. What does the network do with it?
It uses the error signal to adjust those weights and biases on the connection.
To try and do better next time.
Precisely. The math behind it allows the network to figure out how much each weight and bias contributed to the error and adjust them in a direction that should reduce the error on the next forward pass with similar data.
So it's tweaking its own settings based on feedback.
That's the core loop. Forward pass to predict, calculate the error, back propagation to adjust weights and biases. Repeat many, many times with lots of data.
That's really cool. Trial and error, but super methodical. The crash course had that car truck example to illustrate this. Right?
Yeah, that's a good one. Imagine we have data on vehicles, say, their weight and how much stuff they carry. And we know if they're a car or a truck. We want to train a network to classify new vehicles.
Okay, so weight and goods carried are the inputs.
Right. First, we initialize the network with random weights and biases, just random numbers to start.
Okay.
Then we take the first data point. Vehicle weight 15, goods 2, and we know it's a car. Feed 15 and 2 into the input layer.
It goes through the forward pass.
Yep. Multiplied by the random weights, add the random biases through the activation functions, and let's say the output layer predicts truck with higher probability.
Which is wrong. It was a car.
Exactly. So now backpropagation kicks in. We calculate the error using the loss function, predicted truck versus actual car.
And send that error back.
Send it back. The network uses that error to adjust those initial random weights and biases slightly, nudging them in a direction that would have made the car prediction more likely.
So the random settings get a tiny bit less random, a bit more informed.
You got it. And that was just one data point. We repeat this whole process, forward pass, error calc, back prop for the next vehicle in our data and the next, and so on, through the entire data set.
And you do this over and over.
Usually many times over the whole data set.
Yeah.
Each pass helps refine the weights and biases, making the network gradually better at distinguishing cars from trucks based on weight and goods carried.
More data generally means better predictions then.
Generally, yes. But there's a catch we mentioned earlier, overfitting.
Right, the memorization problem.
Yeah. Train too long on the same data, and the model might just memorize the training examples, noise and all. It gets amazing scores on data it's seen, but tanks on new, unseen data because it hasn't learned the general pattern, like cramming for a test versus actually understanding the subject.
Okay, definitely something to watch out for. So that's the basic learning process. Now the source dives into some key terms that kept popping up. Let's start with those activation functions again. Why are they so critical, and what are the main types?
Activation functions are super important for two main reasons. One, they decide if a neuron should activate or fire, basically passing on a strong signal. Two, and this is crucial for deep learning, they introduce nonlinearity.
Nonlinearity. Why is that important?
Because real-world data is messy and complex. If you just stack linear functions, no matter how many layers deep you go, the whole network is still just doing a simple linear transformation. You can't model complex patterns. Nonlinear functions let the network learn much more intricate relationships in the data.
Okay. So nonlinearity is key for complexity. What were some early ideas for activation functions? The source mentioned the step function.
Yeah, the step function was a basic idea. Output 1 if the input is above a certain threshold, output 0 otherwise, like an on-off switch.
Simple. Problems.
Well, it's not great for classification with multiple outputs because you might get multiple neurons outputting one. How do you pick? Also, the sharp on-off makes training difficult using gradient-based methods like backpropagation.
Okay, so step was too simple. What about a linear function, just output and input?
People tried that. It gives you a range of outputs, not just 0 or 1. But the big problem, as the source points out, is it's linear.
Right, stacking linear layers is still just linear.
Exactly. It defeats the purpose of going deep. Also, its derivative, the slope, is constant, which limits how well the network can adjust weights during backpropagation.
So linear is out for deep networks. That brings us to sigmoid, right? The S-shaped one.
Yeah, the sigmoid function. It's nonlinear, squashes the output nicely between 0 and 1, which is great for probabilities, and it has a smooth curve, which helps with gradients.
Yeah.
It was super popular for a long time and still used.
But not perfect. The source mentioned a drawback.
The main one is the vanishing gradient problem.
Vanishing gradient.
Look at the sigmoid curve. At the far ends, where the input is very large or very small, the curve becomes almost flat.
Okay.
That means the gradient, the slope, becomes tiny, almost 0. During backpropagation, these tiny gradients get multiplied back through the layers, and the updates to the weights in the earlier layers can become vanishingly small.
So the early layers basically stop learning.
Pretty much. Their weights barely change. That's a big problem for deep networks.
Yikes. Okay, vanishing gradients are bad. What else is there? Ton,
or hyperbolic tangent. It's also S-shaped, nonlinear, allows stacking. Its output is bounded between -1 and 1. It's actually just a scaled and shifted version of the sigmoid.
Better than sigmoid.
It's often preferred because its output is zero-centered, -1 to 1 instead of 0 to 1, which can sometimes help learning. But it also suffers from the vanishing gradient problem at the extremes.
Okay. So both sigmoid and tan have that issue. What about ReLU? That one seems really common now, ReLU.
ReLU rectified linear unit, super simple. Output is the input if the input is positive, and output is 0 if the input is negative. So max, 0, x.
Well, it's kind of linear for the positive part, though.
It is piecewise linear. But the overall function is nonlinear because of that bend at 0. And combining ReLUs is definitely nonlinear, so you can stack layers effectively.
And advantages over sigmoid and tan.
Big ones. First, it's computationally very cheap, much faster than calculating the exponentials in sigmoid or tan. Second, it helps with the vanishing gradient problem for positive inputs because the gradient is just 1.
Okay, faster. Helps with vanishing gradients. The source also mentions sparsity and activation. Sounds fancy.
Yeah, basically, because ReLU outputs 0 for all negative inputs, it means that at any given time, a chunk of the neurons in the network might be outputting 0. They're inactive.
And that's good.
It can be. It makes the network sparse, meaning fewer neurons are firing. This can make the network more computationally efficient and sometimes even helps prevent overfitting, a bit like dropout.
Interesting. But ReLU isn't perfect either, right? The dying ReLU problem.
Right. If a neuron's input consistently becomes negative during training, maybe due to a large gradient update, it will always output 0. And since the gradient is also 0 for negative inputs, that neuron will stop learning altogether. It just dies.
Ouch. Can you fix a dying ReLU?
There are variations. Leaky ReLU is a common one. Instead of outputting exactly 0 for negative inputs, it outputs a very small positive slope, like 0.01 times the input.
So it still has a small gradient even when negative.
Exactly. That tiny slope keeps the neuron alive and allows learning to continue.
Okay, so ReLU seems like a good default maybe. How do you choose?
The source suggests ReLU is often a good starting point because it works well in practice and is efficient. Sigmoid might be specifically chosen for the output layer in binary classification because of its 0 to 1 range. Tan is another option. Often it involves some experimentation. But the main point is, you need nonlinear activation functions for deep learning to work on complex problems.
Got it. Nonlinearity is essential. Okay, next term. Loss functions. We touched on this measuring the error.
Exactly. Super straightforward concept. The loss function, sometimes called a cost function, just quantifies how far off the network's prediction was from the actual target value. Lower loss means better prediction.
And there are different ones for different tasks.
Yep. The choice depends on what you're trying to predict. For regression, predicting numbers, you might use mean squared error, MSE, or mean absolute error, MAE. For binary classification, like spam not spam, binary cross entropy is very common. For multi-class classification, like digit recognition 09, you use categorical cross entropy.
Okay, so the loss function measures the badness of the prediction. What connects that back to adjusting the weights? That's the optimizer.
Exactly. The optimizer is the algorithm that takes the loss value and uses it to update the network's parameters, the weights and biases, in order to minimize that loss.
The source had that cool analogy. Descending Mount Everest blindfolded.
Yeah. Your goal is the bottom of the valley, minimal error. The loss function is like your feet telling you the slope of the ground right where you are. The optimizer is the strategy you use to decide which way to step downhill.
Nice analogy. And the most common strategy, the granddaddy, is gradient descent.
Gradient descent, yeah. It's the foundational optimization algorithm. It iteratively adjusts the parameters in the direction that reduces the loss the most steeply.
How does it know the steepest direction? Gradients again.
Yep. The gradient of the loss function with respect to the parameters tells you the direction of the steepest increase in loss. So the optimizer takes a step in the opposite direction, the negative gradient, to decrease the loss.
Makes sense. Step downhill. But the source mentioned getting stuck in a local minimum. What's that?
Imagine the loss landscape isn't just one smooth valley, but has lots of little dips and bumps. A local minimum is the bottom of one of those small dips, but it might not be the lowest point overall, the global minimum. Gradient descent might find its way into a local minimum and stop there, thinking it's found the best solution when a better one exists elsewhere.
Ah, okay. Can you avoid getting stuck?
Well, one factor is the learning rate.
Right, the learning rate, how big a step you take.
Exactly. It's a small number that scales the size of the step you take in the negative gradient direction. Too large a learning rate, and you might leap right over the minimum, maybe even bouncing back and forth.
Overshooting.
Right. Too small a learning rate, and training can be incredibly slow, and you're more likely to get stuck in the first local minimum you find. Finding a good learning rate is crucial, often requires tuning.
A balancing act. What about stochastic gradient descent, SGD? How's that different?
Standard gradient descent calculates the gradient using the entire training data set for every single step. If you have millions of examples, that's incredibly slow and computationally expensive.
Okay, yeah.
SGD speeds things up dramatically. Instead of using the whole data set, it estimates the gradient using just one randomly chosen training example or a small batch of examples for each step.
So it's faster, but maybe less accurate per step.
It's noisier, yeah. The steps bounce around a bit more, but it's much faster overall, and that noisiness can actually sometimes help it escape shallow local minima. SGD often includes momentum too, which helps smooth out the steps and speed up convergence.
So SGD is like a more efficient, maybe slightly jumpier version. The Free Code Camp course mentioned other optimizers too, Adagrad, RMSprop, Atom. Briefly, what do they do?
They're basically more advanced variations of SGD that try to be smarter about adjusting the learning rate. Adagrad adapts the learning rate differently for each parameter, making bigger updates for infrequent features. RMSprop improves on Adagrad by using a moving average of squared gradients. Atom combines the idea's momentum, like SGD with momentum, and adaptive learning rates, like RMSprop.
So they try to automatically tune the step size.
Kind of, yeah. Atom is super popular now, often a good default choice.
Yeah.
But the goal of all optimizers is the same. Find the parameter values that minimize the loss function. Sometimes you just have to try a few and see what works best for your specific problem.
Lots of options. Okay, next key distinction. Parameters versus hyperparameters. This comes up all the time. What's the difference again?
Super important difference. Parameters are the things the model learns from the data during training.
Like the weights and biases.
Exactly. Those are the internal variables of the network. They're adjusted during backpropagation. When you save a trained model, you're saving these learned parameter values.
Okay, parameters are learned. Hyperparameters.
Hyperparameters are the things you, the human, set before training starts. The model doesn't learn them.
Like the learning rate we just talked about.
Yep. Learning rate is a classic hyperparameter. Others include the number of hidden layers, the number of neurons in each layer, the type of activation function, like RealU or sigmoid, the batch size, the number of epochs.
Ah, so they're like the external settings or configuration for the learning process.
Exactly. You often have to tune these hyperparameters through experimentation, trying different values and seeing what gives the best performance on a validation set.
Got it. Parameters learned, hyperparameters set by us. That brings us to the last set of terms, epochs, batch size, and iterations. These seem related to handling big data sets.
They are. When your data set is too big to fit into memory and process all at once, you need a way to break it down.
Right, so an epoch.
An epoch is one complete pass through the entire training data set, forward and backward propagation for every single example.
Okay, one full cycle through all the data.
But we usually don't feed the whole data set in at once. We divide it into smaller chunks called batches. The batch size is just the number of training examples in one batch.
Like 32 examples or 128 or something?
Exactly. And an iteration is one update step, processing one batch. So you do a forward and backward pass on one batch, update the weights as one iteration.
So how many iterations in an epoch?
It's just the total number of training examples divided by the batch size. The source gave an example. 34,000 examples, batch size 500. That means 68 iterations to complete one epoch.
34,000 divided by 500 is 68 batches.
Got it. And you usually train for multiple epochs.
Oh yeah, often many epochs. The model needs to see the data multiple times to learn the patterns effectively. Think of it like rereading song lyrics to memorize them.
Good analogy.
But again, too many epochs can lead to overfitting. You have to find the right balance.
So choosing batch size, number of epochs, more hyperparameters to tune. Exactly. And as the source emphasizes, finding the right combination of network architecture, layers, neurons, and all these hyperparameters, it's often a bit of an art. There's no single magic formula. What works for image classification might be different from what works for text. It takes experimentation and building intuition.
The art of deep learning. I like that. Okay, we've got the core concepts and terms down. Now let's look at the different types of learning approaches our source outlines: supervised, unsupervised, and reinforcement. Starting with supervised, the most common.
Yeah, supervised learning is probably what most people think of first. It's all about learning from labeled data.
Labeled data meaning?
Meaning, for every input example in your training set, you also have the correct output or label. Like for an image, the label might be cat or dog. For an email, spam or not spam. There's a supervisor providing the right answers during training.
So the goal is to learn a mapping from input to the correct output.
Exactly. Learn that mapping from the labeled examples so that later, when you give it a new unseen input, it can predict the correct output label.
And the source breaks supervised learning into two main types: classification and regression.
Classification is predicting a category, a discrete label. Is this email spam or not spam? Binary classification, 2 classes. What handwritten digit is this image? 0, 1, 2, up to 9. Multi-class classification.
Okay, and common algorithms for that.
Things like logistic regression, support vector machines, SVMs, decision trees, k-nearest neighbors, random forests, and of course neural networks can do classification.
Got it. Categories classification, what about regression?
Regression is predicting a continuous numerical value, not a category, but a number. Like predicting house prices based on square footage, or predicting a student's test score based on hours studied, or forecasting sales figures.
So predicting a quantity.
Right. The transcript mentions the basic linear regression equation, y(mx plus b), finding the best line to fit the data. Deep learning can obviously handle much more complex regression tasks too.
Okay, classification for categories, regression for numbers. And supervised learning is used all over it.
Oh yeah. The transcript mentions bioinformatics, like fingerprint or face ID on your phone, object recognition in photos, spam filters, speech to text. Lots of applications rely on supervised learning.
Makes sense. Okay, next type. Unsupervised learning. How's that different? No supervisor.
Exactly. With unsupervised learning, you don't have labeled data. You just have the input data itself. The goal isn't to predict a specific output, but to find interesting structures or patterns within the data. It's more about discovery.
Discovering patterns. Like what?
2 main types mentioned are clustering and association.
Clustering.
Clustering is about grouping similar data points together. Finding natural clusters or segments in your data where the items within a cluster are similar to each other and different from items in other clusters. Think customer segmentation or finding anomalies.
Okay, grouping similar things, algorithms for that.
K-means is a classic one. Hierarchical clustering is another where you build nested clusters.
Got it. And the other type was association.
Association rule learning. This tries to find relationships or rules between items in large data sets. The classic example is market basket analysis.
Ah, the supermarket thing. If you buy X, you often buy Y.
Exactly. Analyzing transaction data to see, like, people who buy diapers also tend to buy beer. Or, as the video course said, potatoes and burgers might lead to beer. Tomatoes and cheese might lead to pizza bread. Finding those co-occurrence patterns.
Useful for recommendations, I bet.
Totally. Amazon's customers who bought this also bought. It's a prime example. Airbnb uses unsupervised learning for recommendations too, grouping similar listings or user preferences. Fraud detection often uses it to spot unusual transaction patterns that don't fit known clusters.
Cool. So supervised learns from labels, unsupervised finds patterns in unlabeled data. What about the third one? Reinforcement learning. That always sounds the most like sci-fi learning.
Yeah, it's pretty different. Reinforcement learning, RL, is about an agent learning to make decisions by taking actions in an environment to achieve some goal.
Agent environment.
Right. The agent learns through trial and error. It performs an action, the environment gives it feedback in the form of a reward if it was a good action towards the goal, or a punishment if it was bad.
So it learns from consequences.
Exactly. The goal is for the agent to learn a policy, basically, a strategy for choosing actions in different situations, states, that maximizes its total cumulative reward over time.
How does that compare to the other two?
Well, unlike supervised learning, nobody tells the agent the right action explicitly. It just gets reward signals. And unlike unsupervised learning, there is a goal maximizing reward. It's not just about finding patterns. It's often modeled using something called a Markov decision process, MVP.
Okay. The source used Pac-Man as an example.
Perfect example. Pac-Man is the agent, the maze is the environment, Pac-Man's location is the state. Eating dots gives a positive reward. Getting caught by a ghost is a negative reward, punishment. The goal is to learn a policy, which way to move, to eat all the dots, maximize reward, while avoiding ghosts.
Learning by playing the game and seeing what works.
Pretty much. Through many trials, it figures out strategies to get the highest score.
What are real-world uses for RL?
It's got huge potential. Robotics is a big one, teaching robots to walk or manipulate objects. Game playing, obviously. But also things like optimizing traffic light timings, designing business strategies, controlling complex systems like power grids or chemical plants, even personalized web recommendations.
Wow, okay. So 3 distinct ways machines can learn. Now, let's circle back to that challenge we mentioned, overfitting. Why is it such a persistent problem?
It's just fundamental to how these models learn. They're so good at finding patterns, they can easily find patterns in the noise or specific quirks of the training data, not just the underlying generalizable signal.
So it fits the training data too well.
Exactly. The model gets complex enough to essentially memorize the training answers. The source used that graph analogy. Imagine plotting data points. An overfit model draws a super wiggly line that hits every single point, even the outliers.
But that wiggly line won't predict new points well.
Right. A simpler, smoother line that captures the general trend, but maybe misses a few training points, will actually generalize better to unseen data. That's the goal.
Okay, so how do we fight overfitting? The source listed several strategies. More data is best.
More data is almost always the best defense if you can get it. More diverse examples help the model learn the real patterns, not just the noise in a small sample. But often, getting more data is hard or expensive.
So what else? Regularization.
Yep, regularization techniques are key. They basically add constraints to the learning process to discourage the model from becoming too complex and memorizing the training data.
What kind of constraints? Dropout was one mentioned.
Dropout is a really clever and effective one. During each training step, you randomly drop out, temporarily disable a fraction of the neurons in the network, along with their connections.
Just turn them off randomly?
Yep. It means the network can't rely too much on any single neuron, because it might disappear at the next step. It forces the network to learn more robust, redundant representations. It's like training lots of slightly different, smaller networks simultaneously.
Interesting way to force robustness.
Yeah.
What else? Data augmentation.
Data augmentation is huge, especially for images. You take your existing training images and create new, slightly modified versions. You might rotate them a bit, shift them, zoom in or out, flip them horizontally.
Creating more data artificially.
Essentially, yeah. It teaches the model that the object is still the same even if it looks slightly different. You have to be careful, though don't apply transformations that change the meaning. The source warned about, like flipping a B horizontally makes it a D. You wouldn't want that for letter recognition.
Good point. Okay, dropout, data augmentation.
Early stopping is another common one. You monitor the model's performance not just on the training data, but on a separate validation data set that it doesn't train on. You keep training as long as performance on both the training and validation sets is improving. But if the training performance keeps getting better, well, the validation performance starts getting worse.
That means it's starting to overfit.
Exactly. So you just stop the training process right there before it overfits too much. You save the model from the point where it performed best on the validation set.
Smart. Any other techniques? Weight regularization.
Right, L1 and L2 regularization. These add a penalty term to the loss function based on the size of the weights in the network.
A penalty for big weights.
Yeah. L2 regularization penalizes the square of the weights, encouraging the network to use smaller, more distributed weights, which often leads to simpler, more generalizable models. L1 penalizes the absolute value of the weights, which encourages some weights to become exactly zero. It promotes sparsity, effectively doing some feature selection.
Okay, so different ways to constrain the model's complexity. Lots of tools to combat overfitting.
Definitely. It's a constant balancing act in practice.
All right, moving on to common types of neural network architectures. The source mentions a few key ones. Let's start with the basic. Fully connected feed-forward neural networks.
Yeah, these are often called multi-layer perceptrons, or MLPs. They're kind of the vanilla neural network. Fully connected means each neuron in one layer is connected to every neuron in the next layer. Feed-forward means information only flows in one direction. From input to output, no loops or cycles.
So the standard structure we've been talking about mostly.
Pretty much.
Yeah.
Input layer, one or more hidden layers, output layer. Uses activation functions like we discussed, RailU, sigmoid, etc. They're very flexible. You can choose the number of layers, neurons per layer, activation functions.
Trade-offs.
Bigger networks, more layers, more neurons, can model more complex functions, but need more data, more compute power, and take longer to train. Also, they're not great at handling sequential data, where order matters.
Right, because each input is treated independently.
Exactly. They don't have any built-in memory of past inputs. Which leads us to
Recurrent neural networks, RNNs.
right. RNNs are specifically designed for sequential data. Things like text, speech, time series data, where the order of elements is crucial.
How do they handle sequences?
The key idea is a feedback loop. The activations from the hidden layer at one time step are fed back into that same hidden layer at the next time step.
So it has a memory of what it just saw?
Kind of, yeah. A short-term memory. It allows the network to use information from previous elements in the sequence to help process the current element. Think about understanding a sentence. The meaning of a word often depends on the words that came before it.
Like the sources example, the clouds are in the burk, expect sky. RNNs can capture that dependency.
That's the idea. They can process sequences of varying lengths and theoretically capture long-range dependencies. They also use parameter sharing. The same set of weights is used at each time step, making them efficient.
Sounds powerful for sequences. Downsides.
The basic RNN structure struggles with long-term dependencies due to those vanishing and sometimes exploding gradient problems we talked about earlier. The signal from many steps gets diluted.
So the memory is quite short-term in practice.
In simple RNNs, yes. That led to the development of more sophisticated variants like LSTMs, long short-term memory, and GRUs, gated recurrent units.
LSTMs and GRUs.
Yeah, they have internal gates mechanisms that control the flow of information, allowing them to selectively remember relevant information over much longer sequences and forget irrelevant stuff. They're much better at capturing long-range dependencies.
So RNNs, especially LSTMs and GRUs, are the go-to for text, speech, time series.
Definitely. Natural language processing, machine translation, sentiment analysis, speech recognition, lots of applications.
Cool. Okay, last major architecture. Convolutional neural networks, CNNs, what are they good for?
CNNs absolutely dominate in computer vision tasks. Image recognition, object detection, image segmentation. Also used for video analysis and even some NLP tasks. They're inspired by the human visual cortex.
Inspired by how we see. How do they work?
The core building blocks are different from standard feed-forward or recurrent nets. They use specialized layers, convolutional layers and pooling layers.
Convolutional layers.
Imagine sliding a small filter, or kernel, across the input image. This filter is looking for a specific simple pattern, like an edge or a corner. The convolutional layer applies many different filters to the input, creating feature maps that highlight where those patterns occur.
So it's detecting basic visual features.
Exactly. Early layers detect simple things like edges and textures. Deeper convolutional layers combine these simple features to detect more complex patterns, like shapes, parts of objects, and eventually whole objects.
Okay, what about pooling layers?
Pooling layers, or subsampling layers, come after convolutional layers. Their job is to reduce the spatial size of the feature maps, making the network more computationally efficient, and also making the detected features more robust to small changes in position or orientation. Max pooling is common. It takes the maximum value in a small window.
So convolution finds features, pooling reduces size, and adds robustness.
Yep. A typical CNN for image classification might look like input, image convolution, pooling, repeat a few times, flattened flat, fully connected layers, output classification.
Stacking those layers builds up complexity.
Exactly. They learn a hierarchy of features, from simple edges to complex objects, which is why they work so well for visual data.
Makes sense. Okay, we've covered concepts, terms, types of learning architectures. Now let's walk through the practical steps of actually doing a deep learning project according to our source. Step 1 seems obvious, gathering data.
Obvious, but absolutely critical. Garbage in, garbage out is very true here. The quality and quantity of your data fundamentally determines how well your model can perform.
How much data do you need?
Depends hugely on the problem. The source gives a rough rule of thumb, maybe 10 times as many examples as parameters in your model. For image classification, it suggests a minimum of maybe 1,000 images per class. But more is generally better, assuming it's relevant and clean data.
Where do people get data?
Lots of places. Public repositories like the UCI Machine Learning Repository, platforms like Kaggle, which hosts datasets and competitions. Google has a dataset search tool. Even places like Reddit can have useful data depending on the project. Or you might need to collect your own.
Okay, so you've got data. Step 2, pre-processing data. Sounds important.
Crucial. Raw data is rarely ready to be fed directly into a model. Pre-processing involves cleaning and preparing it. A key first step is splitting your data.
Splitting. Into what?
Typically 3 sets: training, validation, and testing.
Okay, what's each one?
The training set is the bulk of the data, used to actually train the model, adjust weights and biases. The validation set is used during training to tune hyperparameters, like learning rate, number of layers, and for things like early stopping, it gives an unbiased estimate of how the model is doing on data it hasn't trained on. The testing set is held back completely until the very end, used only once to get a final, unbiased evaluation of the fully trained model's performance on totally unseen data.
So you need that validation set to tune without cheating by looking at the final test set.
Exactly. You also need to make sure the data in all splits has a similar distribution, otherwise your results might be skewed. Techniques like k-fold cross-validation can help make this more robust, especially with smaller data sets.
Okay, splitting is key. What else in pre-processing?
Formatting data correctly,
Right.
making sure it's in a table format like CSV if needed. Handling missing data is a big one, deciding whether to remove samples features with missing values, which uses information, or impute them, for example, fill with a mean or median, which can introduce bias if not done carefully.
Tricky. What about really large data sets?
Sometimes you might need to sample the data to make training feasible, and dealing with imbalanced data is common.
Imbalanced, like way more examples of one class than another.
Yeah, if you're detecting a rare disease, you'll have way more not diseased examples than diseased. The model might just learn to always predict not diseased and get high accuracy, but miss all the actual cases.
How do you fix that?
Techniques include downsampling the majority class, removing some examples,
Right.
or upweighting the minority class, telling the model to pay more attention to those examples during training.
Okay. One more thing mentioned was feature scale.
Right. Making sure all your input features are on a similar scale.
Right.
If one feature ranges from 0 to 1 and another from 0 to 1 million, the larger scale feature can dominate the learning process. Common methods are normalization, scaling to a 0-1 range, and standardization, scaling to have 0 mean and unit variance. It helps many algorithms perform better and converge faster.
Phew. Lots involved just in preparing the data. Okay. Step 3. Building and training the model. This is where the neural network comes in.
Yep. You take your pre-processed training data, choose your network architecture, V4, CNN, RNN, etc., set your hyperparameters, and start the training loop we discussed. Forward propagation, calculate loss, back propagation to update parameters, repeat for many epochs.
Step 4. Evaluating the model, using that validation set.
Exactly. After training, or during for early stopping, you evaluate the model's performance on the unseen validation set using appropriate metrics, like accuracy, precision recall, F1 score for classification, or MSE for regression. This tells you how well it's likely to perform in the real world.
And if it's not good enough, step 5, optimizing the model.
Right. This is where you go back and tweak things. Mostly it involves hyperparameter tuning, adjusting the learning rate, changing the number of layers or neurons, trying a different optimizer or activation function, maybe increasing the number of epochs. It's often an iterative experimental process.
And readdressing overfitting if that's the problem.
Definitely. If your evaluation shows high training accuracy but poor validation accuracy, you need to apply those regularization techniques. Get more data if possible, add dropout, use data augmentation, implement early stopping, try L1, L2 regularization, or maybe simplify the model architecture.
Seems like you could tweak forever.
You could. That's why it's important to define what good enough performance looks like for your specific problem. Optimization is about reaching that target, not necessarily achieving perfection.
Makes sense. Okay, that covers the whole project lifecycle. Wow, we've covered a ton of ground.
We really have. From the basics of AI and ML through neural networks, key terms, different learning types, architectures, and the practical steps.
So wrapping up, the key takeaway is that deep learning, built on these neural networks, learns patterns directly from data through this process of forward and back propagation, adjusting its internal parameters.
Right, and understanding the fundamentals, activation functions, loss functions, optimizers, the different learning paradigms and architectures like CNNs and RNNs gives you a really solid base.
It can definitely seem complex, but hopefully breaking it down like this makes it feel more accessible.
Absolutely. This was obviously an introductory overview. There's so much more depth to each of these topics.
For sure, but it's a great starting point. So maybe a final thought for our listeners, especially Gen Z, to mull over.
How about this? Think about all the deep learning systems shaping your daily online world right now. The videos you see, the music suggested, the news filtered, the products recommended.
Yeah, it's everywhere.
So how might really understanding how these systems work, even at this fundamental level, empower you? Not just as a user navigating this stuff, but maybe as someone who could build better, fairer, or more creative systems in the future.
That's a great question. Moving from just being influenced by the algorithm to understanding it, maybe even shaping it.
Exactly. If something here sparked your interest, maybe CNNs for images, or RNNs for language, or the ethics around AI, definitely dive deeper into that specific area. There are tons of resources out there.
For sure. Well, hopefully this deep dive gave everyone a clearer picture of what deep learning is all about and why it's becoming such a crucial part of our world. Thanks for unpacking it all.
My pleasure. It's fascinating stuff.